Ujú. Bienvenidos a todos a la presentación de la profesora Wyong Lee. Voy a hacer una pequeña introducción y presentación. La profesora Wyong Lee, ella es originalmente una profesora de matemáticas de enseñanza básica y media en Seúl, Corea del Sur. Es profesora asistente en Texas State University y obtuvo su doctorado en educación matemática en la Universidad de Georgia. Sus intereses principales de investigación incluyen la construcción de modelos mentales del razonamiento matemático de los y las estudiantes, específicamente la construcción y uso de sistemas coordenados por parte de los y las estudiantes en relación a su pensamiento espacial y cuantitativo. Y también está interesada en aprender cómo los y las profesoras pueden facilitar y apoyar el razonamiento matemático de los estudiantes. Vamos también a estar haciendo la introducción un poquito en inglés también. Professor Wyong Lee, she is a former middle school and high school math teacher from Seoul, South Korea. Is an assistant professor at Texas State University. She obtained her PhD in mathematics education at the University of Georgia. Her main research interest is in building conceptual models of how students think mathematically, specifically students' constructions of and use of coordinate systems involved in their spatial and quantitative reasoning. She's also interested in learning how teachers can facilitate and support their students' mathematical thinking. Today, she's going to be presenting her work, and I'm going to let her continue with the presentation. Ella va a presentar su trabajo hoy día y ahora voy a dejar a la profesora Wyong Lee para que empiece su presentación. Wyong,
thank you.
You can start.
Yeah, thank you so much for the introduction, Dario. Before I start, I just wanted to share with you all here that I met Dario in graduate school at the University of Georgia. And during that time, I was always very much inspired by his academic curiosity, his very well-articulated thoughts and questions, and his passion for education. So it is a great honor to be here today to meet some of his colleagues, and I don't know if there are any students of his as well, and share my research. So I thank you for the opportunity. Okay, so
Thank you.
So I just want to first give you an overview of my talk for today. I will start out with some motivation behind my work, why I became interested in the work that I do, and then introduce you kind of broadly to my research activities. And then today I wanted to dive into some theoretical frameworks that I've been developing and a textbook analysis project that I did with a graduate student here at Texas State, and then end with a discussion based on some findings from this project. Okay, so this is just kind of the outline of today's talk. And please stop me between the talk if you have any questions or comments as we move along, so that this talk could be more like a conversation rather than me just talking at you. Okay, so for the motivation, so let me first start with a pretty general fact that I think everyone here can agree with, which is that graphs are pretty commonly used to model, communicate, and analyze phenomena in STEM fields, right? I think we can all agree with that. Graphs are a pretty predominant way of communicating in STEM fields. However, on the other hand, research has shown that students experience difficulties as they engage in constructing or interpreting graphs. And as you can see in these references, these findings range from back to 1992 until even very recently, right? This is something that researchers continue to show, that students have difficulties with graphs. And so this was something very intriguing to me. And I wanted to look into why students have such difficulties or challenges with graphs. Okay, so this was kind of the motivation behind my work. But when I looked into the research literature, I noticed that in the literature on students' graphing activity, many researchers assume the Cartesian plane as given, meaning that they would just, mostly focus on the graph itself and not really think much about how students were thinking about the Cartesian plane. I also noticed that in curricula, the Cartesian plane is often taken for granted, and students are assumed to develop proficiency in using the Cartesian plane in a relatively unproblematic ways. Meaning, oftentimes students are told how to make a Cartesian plane, but after that, they're kind of expected to know how to use it in multiple mathematical domains. And so my research has focused on understanding how students construct and make sense of coordinate systems, which I view as the foundational structure underlying graphs, because I thought that maybe that might help us explain some of the difficulties that students might have with graphs. Okay, so this is kind of the motivation behind how I came to become interested in coordinate systems. So here's an introduction to my main research activities. I'm going to just give you a very broad overview. And to do that, first, let me explain what I mean by a coordinate system, right? So when I say coordinate system, I mean a representational space in which quantities are coordinated to systematically organize some kind of either real world or mathematical phenomenon, okay? And I use the word representational to mean mental constructs that can but do not need to actually have to be physically represented, right? So it doesn't mean that a coordinate system is not necessarily something on a piece of paper. It could be something that's happening in the student's head, okay? There are some assumptions that I make when I do my research, which are that a coordinate system does not represent by itself. It must be created and interpreted by individuals, right? It's not like coordinate systems just exist out there in the world. It has to be, involved in some human activity, and that coordinate systems are constructed by an individual in goal-directed activity, meaning that there must be a reason why people, right, individuals construct or use coordinate systems. So these are some baseline assumptions that I take when I'm doing my research. Okay. So my research, some of the questions that I've been trying to answer through my research activities are as the following. So for instance, I have been interested in looking at how students come to construct coordinate systems. And what I mean by that is I am very interested in looking into how students establish frames of reference. By that, I mean, how do they think about orienting structures? So for instance, if I want to measure the distance of something, what do I take as my reference point? In which direction do I measure something? So on and so forth. So I'm really interested in how students think about frames of reference, how they construct measurements using their frames of reference, right? How do they measure length? How do they measure angle measure? How do they measure these various things and coordinate their measurements to locate objects in space? So typical tasks that I've been using with students are, these are some pictures of the tasks that I've been using. So just to kind of illustrate, if you look at the right hand picture, there's a fish tank right there. And so I would give these fish tanks to the students and just say something like, tell me how you can locate the fish in the fish tank. So those are the types of questions that I would ask students. So through their activity, I tried to see what they would choose as a reference point, how they define directionality, what kind of measurements they want to measure, and how they put all those things together to create coordinate systems. Okay, I'm hoping that that makes sense. Also, another question that I've been asking more recently in my activity was, okay, so what kind of potential experiences might students have or not have with graphs and coordinate systems in their school experiences, right? And so I've been starting to look into the curricular materials that are used in schools to look at what kind of graphs and coordinate systems are presented in mathematical tasks, okay? So today I wanted to focus on my more recent project. And so I will present a distinction between two types of coordinate systems that has guided my research activities, present results from a textbook analysis of US middle school textbooks using this distinction, and discuss some of the implications for teaching and curriculum development based on the findings. And I also want to acknowledge my collaborators, these three amazing people, because the work that I present today was done in collaboration with these three collaborators. So there's just a little shout out to these people. So I want to now jump into this theoretical framework that has been guiding my research activities. And, essentially what it is making a distinction between different ways that coordinate systems could be used. So earlier I explained that one of the assumptions that I use, that I make in my research, is that coordinate systems must be created or used in some goal-directed activity, right? There must be a reason why an individual uses it or constructs it. And so essentially this distinction is to try to think about, conceptually analyze what different goals a coordinate system might serve for an individual in their mathematical activity, okay? And so there are two different types of coordinate systems that I've been talking about. And I'm going to try to illustrate that through a specific example. So here I have two mathematical tasks. There are both examples that contain a Ferris wheel context within the task. I'm going to give you a couple minutes to read each of these tasks. And I'd like for you, as you read the problem, to think about what are some key differences you notice across each task. What are some differences that you notice from task A and task B? So I'll give you some time to read and think about this. Would anybody like to share some of their observations maybe? You can either type in the chat or just speak out loud in the microphone.
Oh, the first difference I noticed was that task B, it's considering a vertical distance from the ground. I'm not sure in task A that it's the case.
Mm-hmm. Yeah, so you're noticing that the task is attending to different quantities, right? Different quantities are involved in solving the problem. Anything else?
I don't want to take all the other different notice that I don't know if this makes sense, but yeah, it's the same thing that Flavio is saying on the chat. Exactly.
Ah, yes. Second one is dynamic, whereas the first one is pretty static, right? It's just like, boom, one moment of the Ferris wheel and we want to locate the car. Whereas in the second one, we're thinking about the motion of the Ferris wheel, right? There's definitely that difference as well. I mean, there are a multitude of differences across these two problems, even though they're using the exact same Ferris wheel as a context in the problem, right? Now, today, the difference that I want to focus your attention on specifically is this. So if we think about it in task A, a coordinate system is superimposed onto the Ferris wheel space. So we have this Ferris wheel, and what we're doing is we're trying to overlay a coordinate system onto that space so that we can locate the car on the Ferris wheel, right? Whereas in task B, it's slightly different. To graph this situation, a coordinate system is no longer overlaid directly onto the Ferris wheel context, but we're extracting these two quantities from the Ferris wheel space, and we have to produce a totally new, different space where we can coordinate the two quantities. Does this make sense to everybody? Yeah, so in task A, we have the Ferris wheel, we're gonna go boom, overlay the coordinate system onto that space, whereas in the second case, now we're taking these quantities out from the context and producing a totally new space where we're going to coordinate and think about the relationship between the two quantities that were extracted from the situation. And so this is really the essence behind the distinction that I'm trying to illustrate today. Okay, so let me unpack this a little bit more. So the distinction between two types of coordinate systems is based on a conceptual analysis that colleagues and I have made to think about the different goals that a coordinate system could solve, to serve, right? And so in the context like task A that we just saw previously, I refer to the coordinate system as a spatial coordinate system. A spatial coordinate system is a coordinate system overlaid onto some physical or imagined space being represented, and the objects within that space are being tagged with coordinates, with quantities. So in this case, the coordinate system quantitatively organizes the space in which the phenomenon is situated. Okay. So if you think about task A as an example, you can see here we have this Ferris wheel right here. We have the Ferris wheel. And then we have these orienting structures, these axes that we have established so that we can think about two quantities, the horizontal displacement and the vertical displacement, right? The horizontal and the vertical displacement from the axle, the reference point, so that each car's location could be tagged with two quantities, the distances, right? So that each car could be quantitatively located through this coordinate system. So this is an example of when we might use a coordinate system in a spatial sense. Now, on the other hand, in contexts like task B, I refer to the coordinate system as a quantitative coordinate system. What I mean by that, a quantitative coordinate system is a geometrical representation of the product of measure spaces. And constructing a quantitative coordinate system involves an individual to establish quantities within the given space or phenomenon, but then extract those quantities from the situation and then project them onto some new space, which is totally different from the space in which the quantities were originally conceived. So let me illustrate this again using task B. What I mean by that is, so if we look at this example that we just read in the problem, in order to solve this problem, the individual needs to first establish the vertical distance from the ground as a quantity, extract that from the situation and project that onto a number line. Also establish time as a quantity, extract that from the situation and project that onto a number line. And then arranging those number lines orthogonally, putting them together, we can produce a totally new space, a new product space that was made by these two measures, which is different from the space in which the Ferris wheel is moving, right? So looking across to summarize the difference between these two, in a spatial coordinate system, situational quantities are coordinated to locate and or describe a point in the same or analogous space in which the phenomenon occurs, whereas in a quantitative coordinate system, a point is constructed via coordinating quantities disembedded from or extracted from the space in which the phenomenon occurs. So they are very different in nature. Now, you might be wondering, well, they both involve quantities. Why are you calling one spatial and why are you calling the other one quantitative, right? So I want to acknowledge and clarify that both types involve coordinating quantities. However, the context in which the coordinate system is conceived of is captured by its names. So in a spatial coordinate system, you're starting with a space that you want to organize. But in a quantitative coordinate system, you start with the two quantities that you want to coordinate. So that's kind of the main difference between the two types of coordinate systems. Now, here's a question that you might be wondering, why do we care about this distinction? What does this distinction do for us? So graphs constructed upon each coordinate system type may entail totally different meanings due to the nature of the coordinate system. Because of the different ways, the different purposes that each coordinate system can serve, the graphs may entail totally different ways of reasoning. So to unpack that a little bit, what I mean by that is a graph within a spatial coordinate system, because of the way that the spatial coordinate system is constructed, it could be viewed as a collection of objects or traces of an object within the space containing the original objects or phenomena. On the other hand, a graph within a quantitative coordinate system is a collection of points representing relationships between extracted magnitudes. So no longer can we view graphs as projections of the actual physical objects or phenomena from the original space. Let me explain this a little bit further with specific examples. So let me show you two different tasks, okay? Let's first take a look at this task that I pulled from a middle school textbook. In this task, I'll first give you a moment to read it real quick. So if I ask you to decide whether this would be an example of a spatial coordinate system or a quantitative coordinate system, which one would you classify this as?
I would say spatial.
Right, and why did you say that, Dario?
Because the quantities that we are talking about are in the coordinate system, so to speak, I guess. Yeah.
Yeah, exactly. Like, so what we're doing is we have this park space, and all we're doing is we're overlaying a coordinate system onto that space so that we can describe the different, locations within the park, right? And so this red line segment here is the path that the person is taking, right? And so this graph that is produced by making that line segment, that red line segment, is the literal path that the person is taking while they're moving within this park, correct? Okay, now let's take a look at this example. I'll give you a second to read this one. Elena, I saw you kind of nodding. Can I ask you, like, what you were kind of thinking about when you were reading the problem?
I think it's the first example, the quantitative
yeah,
the example, the task A.
Mm-hmm. Yeah, so yeah, this is an example. The second one I was using as an example to illustrate the quantitative coordinate system, exactly. Right? Mm-hmm. Yeah, where you can notice that no longer are we thinking about overlaying a coordinate system onto the machine or the package. Mm-hmm. Now what we're doing is we're taking the time and the number of boxes outside from the situation. So this blue line segment here no longer is a literal path of, it doesn't show us, the trace of the box. It's not the actual movement of the machine. Mm. Do you notice the difference that I'm trying to illustrate between these two graphs? And so based on how the underlying coordinate system is functioning, the graph that is constructed upon each coordinate system has to be interpreted very differently. Exactly. Right? One could be interpreted as a literal path of what's happening in the phenomena, whereas the other one, not much so. Yes, Dario.
Mm-hmm. Oh, I just wanted to, because Flavio wrote something on the chat that it's kind of related to what you were talking about. He's asking if it's necessary in the first type, meaning I guess the one on the left, the spatial coordinate system, it's necessary to have the same units of measure in both facets, I imagine.
Yeah, well, it depends on how you want to coordinate the quantities, right? So for instance, for my students that I've worked with, when I asked them to, locate objects in space, sometimes they would choose a distance, but they would also coordinate that with angle measure. So they can select totally different measurements. So by doing that, they would essentially construct a polar coordinate system. In this example, both of them are using showing distance in meters, but I can see somebody measuring the horizontal distance in centimeters, and measuring the vertical distance in miles. So I don't think that necessarily the units have to be the same. Really,
But
sorry?
I'm sorry, but what about the type of quantity? Do you need that they have the same nature, like they're both distance, or that you can have an example with mix, like let's say, I don't know, like speed and distance?
Yeah, so in the first case, you're talking about the spatial coordinate system, right?
Yes, exactly.
Yes. No, so they there's no need that it has to be the exact same measurement. So some students that I've worked with, they could coordinate a distance along with angle measurement, right? And those are different measurements, but using a radial distance along with a angle measure, you can still locate points from a reference point.
Oh yeah, exactly. Okay.
Yeah. So it doesn't necessarily have to be the exact same measurement, and even if it is the same measurement, I don't think that it necessarily has to be the exact same unit, right?
Yeah, I got it.
Yeah. Okay, yeah, that was a good question. So going back to this distinction, what I'm trying to illustrate through these two examples is that essentially, based on the purpose of the underlying coordinate system, the nature of the graphs could be interpreted very differently, right? And why do I make such a big deal out of this? It seems like a pretty simple distinction, but if we go back to the literature, I want to point out that researchers have identified quite often that one of the difficulties that students have with graphs is because they tend to treat graphs as literal representations of a situation. Okay, what do I mean by this? It means that they make these figurative associations with the shape of the graph and some kind of a physical or visual characteristic of the phenomena that is being graphed. Let me give you a more specific example. So for example, a very typical problem that students are given are to do something like draw a graph that shows the speed and time of a bicycle traveling a hill. And so this is a picture of a person traveling the hill, right? And they're asked to graph the speed, how the speed changes over time. And you might already guess that what students tend to do is then for the graph, they just draw the picture of the hill. Instead of showing how the speed would increase, right, over time. And so this is what I mean by making figurative associations. They would associate the shape of the hill, or the picture of the hill, the spatial hill, with the graph. And many researchers have shown that this is a problem that occurs over and over again in students' graphing activity. Okay, so where am I going with this? Well, the point that me and my colleagues have been trying to make is that one possible explanation for students appearing to treat graphs as literal representations of a situation is not that they are always being wrong. It could be that they are interpreting what a teacher or researcher intends to be a quantitative coordinate system as a spatial coordinate system. Okay. And in such a case, the student may be constrained to reasoning about points and spatial attributes in the graph, as opposed to reasoning about the intended contextualized quantities outside of the perceptually available situation. And so really what we wanted to say is there are indeed contexts in which thinking about graphs in this way is productive and necessary. So instead of criticizing students for doing these things that are not productive, we might actually consider why they're doing such things and when those things might actually be productive and useful. right? Because there are clearly situations where it is needed that students make literal interpretations of the graph shape, which would be in a spatial coordinate system, okay? And so if we think about the graphs in each type of coordinate system, what I want to emphasize here is that different ways of reasoning are involved when constructing and interpreting spatial and quantitative coordinate systems and their associated graphs. So when a student constructs or reasons about a graph, it is important that a teacher or a researcher attends to the purpose of the underlying coordinate system from the student's perspective, right? For example, when a student draws axes, when they draw a coordinate system, the teacher or researcher might examine whether the student is attempting to tag quantities onto a particular phenomenon within the space that it is occurring. In other words, constructing a spatial coordinate system. Or if they are representing magnitudes of quantities extracted from outside of the situation. In other words, if they're thinking about a quantitative coordinate system. Or alternatively, are they just pretty much attempting to reproduce an image of their prior classroom instruction without really being aware of what they're dealing with, right? There are all these different things that students may be thinking about. And so instead of just quickly judging how students are thinking about graphs, it might be actually helpful to think about how they're thinking about the underlying coordinate system. Okay, so that's kind of the big story that we're trying to get through making this distinction between the different two different types of coordinate systems and how the graphs that are constructed upon those coordinate systems could be thought about very differently. Okay. So this is the kind of the theoretical framing, the framework that I wanted to share with you. And so now in using this framework, using this distinction in mind, my research team has looked into middle school textbooks. We wanted to investigate the potential experiences that students might have or not have with graphs and coordinate systems in middle school textbooks. Now, we chose to look into middle school textbooks because after being introduced formally to the Cartesian plane in 5th grade geometry in the US, students start to really actively engage in graphing activity starting in 6th grade here. And so that's why we wanted to focus on grades 6 through 8, as that is kind of the beginning of their graphing activity within textbooks. And so we extracted a total of 2,119 tasks from 4 different major US textbook series for this grade level. And these textbooks, they were chosen to include a variety of curricula, including the Common Core State Standards. They are pretty commonly used textbooks. Some of them are research-based textbooks. You may notice that 2 of them are Texas textbooks. We wanted to include some local standards as well, some local textbooks. So these are the textbooks that we selected. And so what exactly did we want to look into in terms of these textbooks? Well, for each task that involved some 2-dimensional Cartesian graph like this, we wanted to look at these 3 different layers that constituted a graph. We wanted to look at the coordinate system underlying the graph. We wanted to look at the graph itself. And then we also wanted to look at the mathematical content that was involved in each of these problems in textbooks. Okay, so we wanted to look at some different aspects that were playing into a mathematical task or a problem within the textbooks. And let me unpack some of these different things in the next slides. Okay, I feel like I'm moving very fast, so if you have any questions, you can stop me, throw out any questions in the chat. So through our analysis of the tasks, we wanted to address these research questions. We wanted to know what types of coordinate system and graphing activities students are required to do. Are they asked to create something? Are they asked to interpret something that's already given to them? What kind of activities are students engaging in these textbooks? We also wanted to look at what types of coordinate systems. Are they spatial? Are they quantitative? What kind of coordinate systems do students experience through these textbooks? We wanted to know that. We also wanted to know what kinds of coordinate systems and graphing activities were appearing in conjunction with the different types of coordinate systems. So for today's talk, for for today, I just wanted to focus on these two research questions that involve coordinate systems. I'm just going to share you very briefly some of the findings that we have from this project. Before I jump into the findings, I do want to share just a very brief overview of our methods, how we did our analysis. We use the content analysis methodology, which means that we selected and extracted the task, the content from the textbooks. And then we used a specific coding scheme, a predetermined framework for coding. And then we quantitatively analyzed the count and the trend in our codes. Okay, now there were 4 different coding schemes, and these are all the different kind of codes that we used. For today's talk, you only need to focus on these 3 that I colored in red. Okay, so the first code that we looked into was what kind of coordinate system, right? The one that I just spent a lot of time explaining. So whether there was a spatial coordinate system, quantitative coordinate system, or neither. Now, ambiguous meant that the task did not really have a context or a story to it, so that we could not determine whether it was spatial or quantitative, right? So a typical example would be an XY graph. So it would show a XY axis, but they don't tell you what X and Y represents. So we don't know what X and Y is, therefore we coded that as ambiguous, okay? For the second scheme, we wanted to look at the coordinate system activity. What kind of activity is the student required to engage in? Are they asked to label one, create one, do both, or interpret one? And I'm going to show you some more specific examples to explain each of these codes, okay? Now, the third coding scheme that I want you to focus on is the mathematical content domain. So we use the Common Core State Standards mathematical domains to kind of distinguish the different types of mathematical topics that involved graphs. And so these are the 6 different domains that we used for coding. Now, I want to emphasize that we coded each task based on our interpretation of the author's intention in each task. Because we didn't have any students where we sat down with them and we gave them the task and said, how are you interpreting this? We didn't do that. Instead, we said, okay, when we, the researchers, read the task, we tried to interpret what the author's intention was. So that's how we were coding each of the tasks. Okay, so now let me show you 3 examples to illustrate the different codes for coordinate system activity. Here's an example of a labeling task. So you can see that, you know, something is already given to them, but the students are required to actually label what each axis represents. So this is an example of a task that was coded as label, okay? Here's an example of a task that was coded as interpret. Now, why do we call it interpret? It's because the coordinate system is already all constructed for the student. It's all pre-labeled, it is all constructed. Everything is there for the student. All they have to do is use it, right? And so that's why we label this as interpret. Here's an example of a task that that was labeled as create. You may notice here at the very last question here, students are asked to sketch a graph, but you may notice that nowhere in the task are students given a coordinate system, right? So in order to graph this relationship, they have to create the coordinate system on their own. And so this is an example of a problem where students have to engage in creating a coordinate system. Okay. Do these codes make sense to everybody? Yeah, okay. All right. So since I've been talking about the coordinate system activities codes, let me just first show you the results from that. What about to evaluate the construction? Can you explain what you mean by evaluate?
Yeah, I mean, when you study statistical graphs, you have kind of different levels of comprehension of the graph. And one of the highest one is when the students have to evaluate the statistical graph, how it's constructed and if it actually it's informative or not, like that.
Yes, no.
So I wonder if you found those kind of tasks.
Yes, no, that's a really good point. So we did look into what kind of activity was involved in the graph as well. But for today's talk, I was only going to focus on what was required for the coordinate system. So I wanted to keep it just restricted to that. But we have also looked at whether the task was asking the student to draw a graph, draw a graph, or evaluate, or read, or interpret a already pre-constructed graph as well. So that was the fourth code that I didn't talk about, but that is a very important aspect that we also looked at as well. But today I wanted to make my talk within the time, so I was gonna only focus on the coordinate system aspect. Yeah. Okay.
Yeah, I understand. Thank you. Thank you.
Yeah, sure. So yeah, so this is a table that shows the count of, you know, each coordinate system activity organized by grade level. Now, I understand that this is a lot of numbers that probably just doesn't mean, you know, a lot when you just look at it. So I just want to highlight a few things that I think are worth noting, right? So you may notice that here, the majority of tasks involved a pre-constructed, pre-labeled coordinate system, 81%. Is that surprising or not? Maybe, kind of. So we found that 81% of the problems in textbooks already gave students a coordinate system. They were all labeled for them. The axes were already drawn out for them, right? I think that has a pretty strong implication in terms of what kinds of experiences students might have, you know, through their textbooks. Only 16% required creating a coordinate system from students. Right? I think that's something kind of noteworthy. And this trend was pretty consistent throughout each grade level. It's not like there was just one specific grade level where this showed up. It was pretty consistent across all 3 grade levels. Okay. Now, when we looked at the coordinate system type by grade, meaning do students look at spatial coordinate systems, quantitative coordinate systems, or neither, right? This is the trend that we saw within each grade level. So the percentages that you see on the screen here, the percentage shows a percentage within each grade level. So what I mean by that is, if you look at grade 7, for example, 7% of the tasks of the problems use a spatial coordinate system, 66% used a quantitative coordinate system, and 27% within the 7 grade problems use ambiguous type coordinate system. So what are some things that you noticed? Do you notice that more than half of the graphs that students encounter use a quantitative coordinate system? Right?
Yeah.
And then after that, it's next to that is the ambiguous, where it's no context, just, you know, X, Y, decontextualized graphs. And then finally, we have some of the spatial coordinate system tasks. And so let me point out a few things. So if you look at the ambiguous type, the very last one, the ambiguous type coordinate systems, you may notice that as the grade levels increase, they gradually increase, but they're pretty similar to each other, right? It's not like the ambiguous type fluctuates very much. And very clearly, you can see that the quantitative coordinate system type is the most dominant. Now, my research team did not do any fancy significance testing, so we cannot claim the significance of these proportions, but I think just, you know, looking at these numbers, it is pretty clear that the tasks utilize mostly quantitative coordinate systems, right? And so now if we look at the remaining, the spatial, you may notice that there's quite a difference across the grade levels. Do you notice that 7th grade only has 7% spatial coordinate systems, right? And so spatial coordinate systems were most prevalent in 8th grade tasks and least prevalent in 7th grade tasks. So my research team wondered, okay, this imbalance in the number of spatial versus quantitative coordinate systems, could that be because of the different mathematical topics that are taught in each grade level? So we looked further into that. And so this table shows you the breakdown of each mathematical domain for a grade level and the different types of coordinate systems. Okay. And so again, this is a lot of numbers, so I don't expect you to read all of the numbers, but let me just point out a few things for you, okay? So if you look at the mathematical domains, you may notice that the geometry, if you look across geometry, right? And the number system domains, predominantly use spatial coordinate systems. Would you agree with that? Yeah. And if you look at the expressions and equations domain, right, and the statistics and probability domain, and the functions domain, they tend to predominantly use quantitative coordinate systems. Even if you look at statistics and probability, you can notice that it's pretty dramatically, almost all the time, quantitative coordinate systems. Right, which kind of makes sense, because if you think about statistics, oftentimes we're extracting these quantities from some kind of a phenomena, and we're making these graphs to express the relation, what's happening, some kind of a trend, or that kind of stuff. And so it kind of makes sense that in statistics and probability, more likely you would encounter a quantitative coordinate system. So, okay, so I just showed you 3 tables. There are a lot of numbers in them. Let me just summarize a few of the findings that I'm trying to illustrate through these tables. So the story that I'm trying to tell you through these findings is that the task afforded disproportionately less opportunities for students to construct a coordinate system on their own. 81% of the tasks that we looked at gave students already all of what they needed to do. They didn't really give much opportunity for students to construct a coordinate system on their own. And I find that to be pretty problematic, or concerning, let me say. There was an imbalance in the types of coordinate systems, and therefore the different nature of graphs that appeared in the textbooks that we analyzed, right? That was something that I was trying to show you through the findings. Interestingly, we did not find any tasks that explicitly contain multiple types of coordinate systems within the same problem. I thought that was very interesting and kind of surprising as well. And different mathematical domains tend to use different types of coordinate systems, which was not too surprising for us. Okay, so through all of these findings, what are some things that we want to discuss as some implications? Based on our findings, we want to propose the following changes in curricula and relatedly in teaching about coordinate systems to support students' mathematical development. First, we think we need more task drawing from contexts that afford opportunities to develop a more balanced understanding of multiple kinds of coordinate system types. And I'm going to try to explain why a little later. Okay. We also believe that more opportunities for students to create their own coordinate systems and graphs are needed, right? That's something that we found to be lacking in textbooks. We also believe that there needs to be better support in curriculum materials assisting students transitioning from spatial to quantitative coordinate systems. And let me illustrate this last point a little bit more. If you look at the way that the Cartesian plane is first introduced typically in US textbooks, it looks something like this. It is a lot of text, so I don't expect you to read the whole thing, but I want to point your attention to this bolded part, okay? So typically in textbooks, Cartesian plane, the way that they're described is they're described in terms of how to make one. Okay, they tell you to do this, to that. And here, I want you to focus on the way that it is written. How far to travel from the origin in the direction of each axis. This description alludes to a spatial coordinate system. It's kind of setting up the students to think about a coordinate system in terms of a pretty predominantly spatial sense, okay? However, if this is the description, the only description that students encounter, it may hinder their understanding of a quantitative coordinate system, because a quantity overlaid onto a number line may not necessarily always be directly tied to some literal travel, okay? And so if you look at these 2 tasks, this is a very typical task that students are introduced at the very beginning when they learn coordinate systems, right? It's, we're gonna put a coordinate system on a town, and there are these different buildings, and we can, use coordinates to locate these buildings, so on and so forth. But then all of a sudden, they're also expected to think about a graph that looks like this, where the axes are no longer used in the same way as they are used in this context, right? And so there needs to be a little bit more opportunities for students to really think about these different ways that coordinate systems might be being used, and associated with that, how the graphs could be considered or thought about differently in each coordinate system type. Okay, and so that's what I mean by helping students kind of reflect on and think about and help them, assist them in transitioning from being introduced to a spatial coordinate system and gradually transitioning into becoming proficient in using quantitative coordinate systems as well. Okay, so I just want to make some closing remarks. In this study, we specifically focused on 4 US textbook series. And so the findings are restricted to just these tasks that we looked at. And so, you know, future studies might look into different countries, different curriculum materials, and so on and so forth. And actually, personally, as I was preparing this presentation, I was wondering, you know, how are coordinate systems introduced and taught or presented in Chile? I just wanted to ask you all if you can give me some insight into that. I thought that was, you know, something interesting to think about. And future studies can also, I think it would be interesting if we can get students to actually look at these problems and tell us how they are interpreting these tasks as well. So with that, I want to end my presentation and open it up to everybody for any questions or comments.
Thank you so much, Wyong, for your presentation. I'm gonna ask if somebody needs some help with the questions or something like that, interpretation and all that. Thank you so much for the presentation. I really enjoyed it. Bueno, si alguien necesita o quisiera alguna especie de ayuda con interpretación o traducción de preguntas y respuestas, yo estoy más que dispuesto a ayudar. En cualquier otro caso, pueden preguntarle directamente a la profesora Wyong alguna pregunta que tengan. También se la pueden escribir en el chat, si prefieren.
I just have a comment, maybe. It's not a question, actually. Sorry, I'm in a very noisy place. I think it's very interesting what you point out about the need of transition between the spatial coordinate system to the quantitative coordinate system. I think I never thought about it, but I mean I totally agree with you that it's a kind of problem that you don't really have like a differentiation in my comment is about that, but I have also a question. Is what kind of stuff have you seen that could be useful for kind of make this transition?
Yeah.
Do you have an example of something like that we can?
Yes, I actually do. There is a task that my research team has been using. We call it the ant farm task, where we have these two ant farm tubes where we ask the student to imagine an ant around in the and so we give the students the tubes like this and say, how can you come up with a way to locate the ants using one single point? Okay, and so in order to solve this task, what students need to do is not only think about coordinating spatially, but they also need to think about now how they would coordinate the locations of the ants. And also what happens is they go like this and they start thinking about the distance. Okay, but it's also what it involves is now shooting out the locations into the plane, which is pretty much what the transition is needed to move from a spatial to a quantitative coordinate system. Yeah. And so that kind of task where it involves having students think about no longer tagging these coordinates onto the space, but thinking about shooting out into the space to create a new point is pretty much the essence behind those kinds of problems that we've found to be pretty productive. Yeah, but we haven't really seen much like that in textbooks.
Okay, well, thank you.
Yes.
I have another question too. Kind of the going a little back. I wanna add something similar to what Flavio was saying. I never thought about this before. Actually, I really enjoyed the presentation. It was very interesting, the distinction to me. I never thought about it. I was fortunate to like see your research before on construction of a student coordinate system. And I always found it interesting. This distinction, though, is something new. I don't remember seeing it in previous presentation. It was great, and I never thought about it. One thing that I want to add to Flavio's question / comment is there, and I don't know if you have data or evidence to answer this question, but do you think it's there like a preferred way to go about this? Meaning, because in Chile, in my experience, we usually start with the spatial coordinate system. And then without any transition, we move to the quantitative.
Yes. Exactly. Yes.
Right. So a transition is needed, as you and Flavio were discussing. But at the same time, do you think it's a preferred way to go about it? Should it be the other way around, or?
Yeah. So.
Or it doesn't matter? I don't know.
The way that I've been thinking about this is the spatial coordinate system is more intuitive because it's directly building on the spatial reasoning that students can bring into a different context, whereas in the quantitative coordinate system, there's that extra level of disembedding or the extraction or the abstraction that needs to happen from the context. So not only am I, creating this new space and reasoning spatially within that new space, to produce that new space, I need to think about taking out these quantities from the situation and then somehow imagine overlaying the quantity onto a number line. That is very complicated. And it's not as intuitive. Like, for instance, thinking about height along a vertical distance could be pretty intuitive, but if you think about overlaying volume onto a line, that is a 3-dimensional measurement, and you're going to say you're going to overlay volume onto a line, which is very weird. And so the way that some other people like Piaget have been talking about, based on what I've read from their work, it is more intuitive and kind of natural to start with the spatial context and then move to the quantitative. But in terms of data to support that, I have tried to, with my students, I've tried to work on tasks that started with quantitative and then move to spatial and then do the other way around. But my issue was that I can't really claim anything because the students that I worked with were either 9th graders or undergraduate students who already had experience with coordinate systems. So I can't really claim one or the other, but based on my conceptual analysis, that is my hypothesis, is that it's more natural to transition from the spatial to the quantitative.
Yeah, I think it makes much more sense. Yeah. Sorry.
May I ask you something? Because I'm thinking about statistical graph, and in Chile, at least in the early years, I'm talking about like the 2nd to 4th grade, the students are introduced to pictograph and then to bar graph.
Yeah.
So they're not exactly like a coordinate system, but they kind of related to quantitative type of graph, no?
Yeah, no, definitely.
So what about that in the US?
It's very similar here too. Before 5th grade, before they're formally introduced to the Cartesian plane, in statistics, they are introduced to bar graphs. Very similar, yes. But the way that I view bar graphs is that they are, like you said, they're kind of different from 2-dimensional Cartesian graphs, right? It's more like several 1-dimensional graphs put together. And so I didn't really include those in the textbook analysis that we did, but they definitely have those experiences before even being formally introduced to the Cartesian plane.
The Cartesian, yeah.
Very similar, yes. Yeah. And
Okay.
so I'm hoping that my future research, I'm hoping to be able to go and work with third graders up to fifth graders to see how, before receiving formal instruction on the Cartesian plane, how do they think about graphs? That is something that I'm hoping to look into in the future.
Yeah.
Yeah.
That would be interesting. Yeah.
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 No sé si alguien más tendrá alguna pregunta adicional. Anybody
Actually,
else?
I have to go, but thank you very much for your talk. It was very interesting. Hopefully we can see your research. Thank you.
Thank you. Thank you so much.
Chao, Flavio. I do have one more question. It's so the distinction, it was very clear to me that the distinction, it's very important for us educators. Do you think that it also would be useful to make the distinction explicit for the students?
Yeah, that's a great question. And we've been asked that question quite often. So the answer is yes and no. And the reason why yes is because we do think that it's important for students to be able to reflect and be aware of the differences. But no, in the sense that we don't want, teachers to start teaching students, oh, this is spatial, this is quantitative, because it's just another set of names that,
Right.
That might not make any sense to students. Similar to, the CGI framework about the different types of activities in terms of addition and subtraction, that was intended for the teachers to use to help teachers make sense of their students' activities, not for elementary students to learn the different names of that framework. So very similarly, what we advocate is that teachers and researchers become aware of this distinction and try to help students understand it, rather than, teach, oh, this is spatial, this is quantitative, if that makes sense. And so that's our only concern in having teachers explicitly teach these things to their students, if that makes sense.
Right. Yeah, absolutely. Thanks.
That was a good question.
¿Algún otro comentario, pregunta? Ok. Creo que puedo dejarlo hasta ahí. Entonces, muchas gracias a todos por venir. Antes que se vayan, si quisiéramos invitarlos a nuestro próximo seminario, que va a ser el día martes 7 de septiembre, donde Daniela Rojas Bastia va a estar presentando su trabajo de descripción de las prácticas reflexivas de los docentes de educación básica al examinar las evidencias de aprendizaje de sus estudiantes que surgen en una clase de matemática. Quiero agradecer a la profesora Wyong Lee por presentar. Wyong, thank you so much for coming. I really enjoyed your presentation.
Thank you. Thank you for having me. It was great to meet everybody, and it was a great opportunity to share my research. Thank you so much.
Perfect. So that's it. And we hope to see you all in the next seminar. Say hi to Hamilton for me as well.
I will.
Yes.
All right. Well, you take care. Thank you for having me. This was fun.
No, thank you so much. I really enjoyed the presentation. It was great.
Thank you.
It was great. Very interesting.